How many solutions can there be to a system of linear equations? When the unknowns can be real numbers, there can be one solution, there can be no solution, and there can be infinitely many solutions to the system. In this case, we will look at how there will be infinitely many solutions to a system. This system contains the same first two equations as the cases when there was no solution and when there was a unique solution to the system. The third equation is changed, and the initial matrix is as follows. We begin by pivoting on the number in the first row, first column. There are the row operations, and here is the new matrix. Before pivoting again, notice that the third row can be divided by 2. Now let's pivot on the -4 in the second row, second column. Now look at the third row. In the case when there was no solution, we had zeros and then a non-zero number at the end. Here we have all zeros. Well, this reads 0 times x plus 0 times y plus 0 times z equals 0. That is, 0 equals 0. While true, this gives no information about the solutions to the system. So we'll eliminate row 3. Row 1 is divisible by 3. In effect, we now have a system of 2 equations in 3 unknowns. The equations are x plus 4z equals -3 and -4y minus 5z equals 8. We're finished with the row operations. We have the numbers along the main diagonal not equal to 0, and we've pivoted on the numbers 1 and -4. It would be a mistake to pivot on the number -5 in the third column. Whenever a matrix looks as such, and the numbers along the main diagonal are not 0, we're finished pivoting. When you're done pivoting, and you have less equations than unknowns, and no row reading 0 equals a non-zero number, there are infinitely many solutions to this system. How do we present these solutions? You begin by writing the equation for each of the rows. The first row reads x plus 4z equals -3. The second row reads -4y minus 5z equals 8. Next, you solve for the leading variable in each of those 2 equations. The leading variable in that first equation is x. Solve for x in the first equation, and you get x equals -3 minus 4z. Solve for the leading variable in the second equation, the y. When you solve for y in that second equation, you get y equals -2 minus 5/4 z. So the two equations that we're going to work with are x equals -3 minus 4z and y equals -2 minus 5/4 z. Any variable on the right of either of those equations is a free variable. You're free to let it be any number you want it to be. The only variable on the right side is z. Let z equal a, where a represents any number. If z is a, we get a solution to this system in parametric form. It reads x equals -3 minus 4a, y equals -2 minus 5/4 a, and z equals a. To show how we can get a specific solution to this system from those equations, let's let a equal 0. If a equals 0, then x is equal to a -3 minus 4 times 0. X equals a -3. Y equals a -2 minus 5/4 0. Y equals -2. And z equals a, which equals 0. If a equals 4, we get x equals -3 minus 4 times 4, or a -19. Y equals -2 minus 5/4 of 4, that's a -7. And z equals a equals 4. You can check that substituting in either -3, -2, and 0 for x, y, and z, respectively, or -19, -7, and 4, respectively, for x, y, and z, if you substitute those numbers into that system that was given, that they will both satisfy the system. You could see how you can get any number of solutions by just changing the value of a. I'd like to end with another example where you would get an infinite number of solutions. Here we have a system of two equations in the four unknowns x, y, z, and w. There's the initial matrix of that system. Let's pivot on the number 1 in the first row, first column. And then pivot on the number -5 in the second row, second column. We're done pivoting, and now we proceed, as was explained in the previous example. Write down the equation for each row. Solve for the leading variable in each equation. From the first equation, that x equals 26/5 minus z plus 6/5 w. And for the second equation, you get y equals 12/5 minus z minus 13/5 w. Recall that after solving for the leading variable in each equation, that any variable appearing on the right side of an equation is a free variable. Here we have two free variables, z and w. Let's let z equal a and w equal b, where a and b can be any numbers. This gives x equals 26 over 5 minus a plus 6/5 b, and y equals 12/5 minus a minus 13/5 b. Z is a and w is b. This gives the parametric form for the solutions to the above system of equations. Again, you can see how there are infinitely many solutions to this system because you're allowed to let a and b be any numbers. They don't even have to be the same number. You could let a be 0 and b be 1, for example.